just when you thought the AI landscape had settled with the Transformer revolution, the ground is shifting beneath our feet again.
Yeah?
We've seen these incredible models achieve things we once only dreamed of, but now the limitations of that architecture are really starting to become apparent.
Absolutely.
Yeah.
The very strengths that propelled Transformers to the forefront are now revealing inherent bottlenecks as we aim for a more advanced and versatile AI.
And that's exactly where we're headed today. You, our listener, have curated a fascinating set of sources, articles, cutting-edge research, your own deep-thinking notes, all pointing towards what lies beyond the Transformer.
Mm-hmm.
Our mission in this deep dive is to unpack these next-generation AI architectures, to really get a handle on which ones show the most promise, particularly as we consider that ultimate horizon, artificial general intelligence, or AGI.
It's a crucial exploration.
Yeah.
And to truly grasp what's coming, we first need to appreciate just how paradigm-shifting the Transformer architecture has been. Its impact is, well, undeniable.
Okay, let's unpack this a bit. The self-attention mechanism, that was the core innovation, wasn't it?
It really was.
Letting the model dynamically weigh the importance of different parts of the input. It's almost like giving the AI a highlighter, to focus on the key information.
Precisely.
Yeah.
And the ability to process information in parallel. That fundamentally accelerated training, allowing us to build these colossal and, frankly, incredibly capable models we're seeing in action today.
And its reach has been astounding. Natural language processing was the initial triumph, but like you said, its influence spread like wildfire vision, audio understanding.
Yeah, even tackling incredibly complex scientific challenges like protein folding with AlphaFold. Transformers have truly reshaped the AI world.
Right. However, as we push the envelope further, those initial limitations are becoming increasingly restrictive. We're talking about that quadratic complexity of self-attention, that dollar simmer. In practical terms, what's the real-world drag here?
Well, think about it. If you're trying to process something really long, say the entire text of War and Peace, or a super high-definition video, or hours of audio, the computational power and memory needed just balloon. It becomes exponentially more expensive and slower. Many of the sources you shared, particularly those looking at truly long-form content understanding, really emphasize this scaling bottleneck.
Which directly leads to the fixed context window problem, right?
Exactly. While these windows have definitely expanded, there's still finite boundaries. The model can only consider so much information at once, limiting its ability to truly understand overarching narratives or maintain coherence across extended interactions. It's like trying to understand a whole movie by only watching it in 10-minute clips.
And it impacts memory in a fundamental way, doesn't it?
It does. Transformers don't really retain information between different interactions. Their memory is confined to that context window.
Right.
It's more of a fleeting workspace than a persistent, selective memory system like ours.
What's fascinating here, too, is the interpretability challenge.
Oh, definitely.
These models can achieve remarkable results, but often we don't know why they make the decisions they do. That black box nature makes it difficult to debug errors, build trust, especially in high-stakes applications.
Yeah, that trust factor is huge.
And if we look at the bigger picture, training these massive transformer models demands colossal amounts of data and computational resources. The environmental and financial costs are significant.
Huge costs. Plus, the way they learn isn't really continuous.
Right.
If you want them to incorporate new knowledge or adapt to evolving data, you typically have to retrain or fine-tune extensively. They don't really learn on the fly in the same way a human does.
This also brings up questions about their reasoning abilities. While they excel at pattern recognition and generating plausible-sounding text, they often falter with complex logic, understanding cause and effect in novel situations, or, generalizing to completely new domains.
Yeah, it's like they can mimic intelligence without truly understanding it. Which leads us naturally to the long-term aspiration of artificial general intelligence.
Right, AGI.
The recent AGI 25 conference highlighted the intense efforts in this direction. However, a growing number of researchers, as reflected in your sources, are skeptical that simply scaling up transformer-based approaches will get us to true AGI.
The feeling seems to be that we're hitting fundamental limits with the current paradigm.
That's the sense, yeah.
And that brings us to some pretty dramatic predictions in our sources talk of a major pivot away from transformers.
That's bold.
With major AI labs supposedly shifting towards subquadratic models by the end of 2025 and largely abandoning transformers by the end of 2026. That sounds like a seismic shift.
It is a bold forecast, absolutely.
Right.
but it's rooted in that unsustainable computational burden and the inherent difficulties transformers face in selectively processing information and reasoning effectively.
Okay.
The argument is that they simply won't be efficient or intelligent enough to tackle the next wave of AI challenges.
Okay, so if the transformer reign is potentially coming to an end, what are the most promising contenders? That's where these next generation architectures come into play.
Right.
We're looking at things like neurosymbolic AI, liquid neural networks, state space models like Mamba, and then a range of memory-centric designs, capsule networks, and even hyperdimensional computing. It sounds like the AI community is tackling these transformer limitations from a multitude of angles.
They really are. It's a very active space right now.
Let's start with neurosymbolic AI. What's the fundamental idea there?
What's particularly insightful here is the attempt to merge the strengths of neural networks, their ability to learn patterns from data, with the logical reasoning capabilities of symbolic AI.
Okay.
The core principle is integration, creating systems that combine these fundamentally different approaches.
Right.
It's often likened to the dual process theories of human cognition, the idea that we have both fast, intuitive thinking system 1 and slower, more deliberate logical reasoning system 2.
So the goal is to give AI both that intuitive pattern recognition and the ability to think logically and reason step by step. How does that actually translate into architectural designs?
Well, there's several key ways this integration is being explored. One is using symbolic knowledge, rules basically, to guide the learning process in neural networks. Another is having neural networks generate or refine symbolic representations that can then be used by a symbolic reasoner, like we saw with alpha geometry, devising symbolic proofs for geometry problems.
Right, that was impressive.
Then we also have co-processing models where neural and symbolic modules work in tandem, kind of exchanging information. But one particularly effective pattern highlighted in the research is the neuro-symbolic neuro approach.
So a neural network takes in the raw data, transforms it into symbolic representations.
Yep.
A symbolic system performs reasoning based on those symbols, and then the result is fed back into another neural network to produce the final output.
Exactly. That seems to be getting a lot of traction.
Yeah.
Now, where does the field stand as of, say, mid-2025? Research in neurosymbolic AI has really surged since about 2020. There's significant focus on areas like learning and inference, knowledge representation, and logical reasoning.
Makes sense.
However, the sources you provided also point out ongoing challenges, particularly in achieving robust explainability and trustworthiness.
Right, the black box problem again.
And especially in developing metacognitive abilities, the AI's capacity to reflect on and regulate its own reasoning. That's a big one.
That makes sense. So who are some of the key players or initiatives pushing this forward?
We're seeing some really exciting developments. There's the Cocosys neurosymbolic AI chip, the first dedicated hardware accelerator for these hybrid models.
Wow, dedicated hardware already.
Reportedly capable of tackling very complex problems, even at the level of the International Mathematical Olympiad.
Impressive.
SingularityNet's Deep Funding Initiative is offering grants for projects specifically aimed at integrating symbolic logic into deep neural networks to enhance reasoning, interpretability, and the ability to learn from less data. The Alan Turing Institute has a significant project exploring the use of NSAI for building more robust and explainable AI for digital twins of critical infrastructure. And the recent Metacog 25 workshop underscores the growing academic interest in incorporating metacognition into these systems.
It definitely sounds like it's moving from theoretical concepts to tangible implementations. And the range of research papers you mentioned earlier, things like recursive machine for generalization, self-backtracking for LM reasoning, lean theorem generation, even LogGPT. That's a really diverse set of applications.
Absolutely. And when we look at the potential of NSAI, enhanced reasoning really stands out as a key capability.
Right.
You're talking about logical inference, understanding causal relationships, and solving multi-step problems, as exemplified by that hierarchical neurosymbolic decision transformer.
Okay.
And the potential for interpretability is huge. That transparent symbolic layer with its rules and knowledge graphs could be a game changer for building trust in AI systems.
Yeah, definitely.
Plus, the ability to leverage symbolic knowledge means these systems might learn effectively from much smaller data sets, and they could potentially be more robust and better at transferring knowledge to new situations.
But there must be significant hurdles to overcome. What are some of the major challenges facing neurosymbolic AI?
Well, scaling the symbolic components to handle vast, complex, and constantly evolving knowledge is a significant challenge.
Sure.
Then there's the inherent complexity of integrating these two very different paradigms, the continuous representations of neural networks and the discrete nature of symbolic systems. It's not trivial.
Right. Apples and oranges almost.
Kind of. And as we discussed, the metacognition aspect is still in its early stages. Finally, achieving deep and truly reliable explainability that goes beyond just surface-level rule tracing is a difficult problem.
So in the context of reaching artificial general intelligence, where might neurosymbolic AI fit in?
Well, the argument is that by directly addressing abstract reasoning and the manipulation of structured knowledge, and with the potential to develop metacognitive abilities, NSAI offers a potentially more direct pathway to AGI compared to simply scaling up purely neural models. However, as your sources emphasize, significant breakthroughs in integration, scalability, and particularly metacognition are still needed to realize that full potential.
Okay, let's switch gears and explore another very different approach. Liquid neural networks. The name itself suggests something more. Fluid and dynamic. What's the core idea here?
What's fascinating about LNNs is their inspiration. Biological nervous systems, specifically the neural networks of the tiny C. elegans worm.
Oh, interesting.
The fundamental concept is continuous time processing, using ordinary differential equations, or ODEs, rather than the discrete step-by-step computations of traditional neural networks.
Okay, ODs.
This allows for dynamically changing network architectures that can naturally handle data that arrives irregularly over time, which is very common in the real world.
Continuous time and dynamic architectures, that sounds like a significant departure from traditional deep learning. What are the different flavors or types of liquid neural networks being developed?
So we have liquid time constant, or LTC, networks. Here, each neuron has a time constant that can adapt based on the input, effectively controlling its memory span. These often rely on numerical ODE solvers for their computations.
Okay, adaptive memory span.
Then there are closed-form continuous time, or CFT models. These have analytical solutions to their underlying equations, which allows for faster computation and makes them potentially better for real-time application.
Faster, okay.
And neural circuit policies, or NCPs, are characterized by their sparse connectivity and have shown promise in tasks like autonomous flight control, where efficiency is really crucial.
Right.
Think of LTCs as having a flexible memory dial that adjusts how long a past event influences the present, while CFC models are designed for speed, making them ideal for things that need instant reactions.
So who are the leading researchers and institutions working on liquid neural networks? Where's the hub?
The field has strong roots at MIT CSAIL, with key researchers like Hassani, Russ, Lechner, and Amini being particularly influential.
Right, MIT.
And there's now a company called Liquid AI, co-founded by Hassani, that's actively developing what they call liquid foundation models for generative AI, with a strong focus on efficiency for edge computing devices.
Edge computing.
That's interesting,
Yeah,
though.
smaller devices, less power. We've also seen recent research, like a May 2025 paper on using LNNs for inferring knowledge from temporal graphs, and another in April 2025 exploring their application in telecommunications for dynamic wireless environment prediction.
Telecom, okay.
Liquid AI is also focusing on scaling these models and developing more efficient training techniques. And the increasing availability of open source libraries for neural differential equations is a significant boost to the field.
What are the key capabilities that make liquid neural networks stand out? Why are people excited?
Their adaptability and ability to learn in real time are significant advantages. They can continuously adjust their dynamics in response to new data and changing environments.
So more like how we learn. A bit closer, yeah. They also show robustness to noisy and drifting data, which is critical for real-world applications where data isn't perfect.
Definitely.
Because of their continuous time nature, they can inherently handle time series data that isn't sampled at regular intervals without needing complex preprocessing.
Okay, that's useful.
Their computational efficiency and relatively small size make them very attractive for deployment on resource-constrained edge devices.
Right, the edge angle again.
And there's some early evidence suggesting they might be better at learning causal relationships and could offer more interpretable internal representations in certain configurations. It's almost like we're trying to build AI that can not only think, but also feel its way through the world, adapting continuously.
But what are the main challenges? What needs to be addressed for liquid neural networks to see wider adoption?
Well, training complexity can be a significant hurdle, especially the computational costs associated with solving the ODEs and LTC models,
Okay.
and potential gradient instability issues during training. Scaling these models to the size of the massive transformer-based foundation models is also an ongoing challenge.
Right, getting them huge.
We still need a deeper theoretical understanding of their capabilities and limitations compared to more established architectures. And the ecosystem, the toolkits and libraries, is less mature than for transformers.
Sure, it takes time to build that up.
And for specific applications like telecom, achieving strong zero-shot learning capabilities and dealing with latency constraints are important areas of active research.
And when we consider the path to AGI, what potential role might liquid neural networks play?
Their capacity for continuous learning from streaming data, their robustness in dynamic and unpredictable environments, and their ability to handle irregular sensory inputs make them particularly relevant for embodied AGI.
Embodied AGI, right. Robots and such.
Exactly. AI that interacts physically with the real world. Some researchers propose that LNNs could serve as a System 1 type component in a hybrid AGI system, handling the fast, intuitive, and adaptive processing of information.
Interesting. System 1. All right, let's move on to state space models, or SSMs, with the Mamba architecture generating a lot of excitement recently.
Yeah.
What's the core innovation here?
State space models offer a very efficient way to process sequential data, and Mamba has emerged as a particularly compelling architecture in this space.
Yeah, I've heard a lot about Mamba.
Introduced around mid-2024 and continuously being refined, it achieves strong performance on various sequence modeling tasks while boasting linear computational complexity with respect to the sequence length.
Linear complexity. Okay, that's the big deal.
That's the headline, yeah. This is a direct challenge to the quadratic complexity of transformers and the inherent limitations of recurrent neural networks for very long sequences. The key is a selective SSM mechanism with input-dependent gating.
Linear complexity for sequence length, that sounds like a huge leap forward for handling truly long-range dependencies. What are the specific innovations that enable Mamba to achieve this?
The core breakthrough is the selective state scanning mechanism, often referred to as the S6 structure.
S6, okay.
This allows Mamba to dynamically select which information from the past it should retain and propagate forward and which it can forget based on the current input.
So it's selective about memory.
Exactly.
Oh.
This selective processing is crucial for efficiently modeling long-range dependencies. Because of this mechanism, it achieves that crucial linear computational complexity in both computation and memory.
Gotcha.
Furthermore, the architecture is designed with hardware efficiency in mind, optimized for GPUs through techniques like parallel scans and kernel fusion.
Hardware aware. Nice.
And like LNNs, it incorporates input-dependent gating mechanisms to control the flow of information within the model. It's not just about being fast, it's about being selectively intelligent about what information it processes and carries forward.
So it's not just processing everything faster, it's being smarter about what information is actually important to process.
Precisely. And we're seeing Mamba and related SSMs being applied to a surprisingly broad range of tasks already.
Really? Like what?
In natural language processing, they're showing promise for handling very long documents and are even being integrated into mixture of expert models for greater capacity.
Okay, long docs make sense.
In computer vision, architectures like Vim are demonstrating faster processing and lower memory usage compared to vision transformers.
Faster than VOTs. Okay.
And we're seeing specialized versions like HRV Mamba for dense prediction tasks and UMamba for biomedical image segmentation.
Wow, vision too.
They're also finding applications in speech and audio processing, genomics, handling tabular data, time series forecasting, reinforcement learning for in-context learning, generative diffusion models.
It's everywhere.
And even processing graph data with Graph Mamba. Plus, there's a growing trend towards hybrid architectures that combine the strengths of Mamba with transformers.
Hybrids, right, like Jamba.
Exactly. It feels like every time you blink in the AI world, 3 new architectures have topped up, often incorporating Mamba.
That's an incredible scope of applications in such a short time frame. What are the core capabilities that make SSMs like Mamba so powerful?
The ability to handle extremely long contexts efficiently is the most significant advantage. That linear complexity opens up possibilities for processing sequences that would be computationally infeasible for standard transformer models.
Right, breaking that quadratic barrier.
And it's not just about the length. They also offer significant computational efficiency in terms of both speed and memory usage when dealing with these long sequences.
It's cheaper.
And importantly, they achieve a global receptive field, meaning they have the potential to access and integrate information from any point in the input sequence, theoretically.
But as with all architectures, there must be limitations and ongoing research challenges. What are some of those for SSMs?
Well, interestingly, theoretical work from around March 2025 suggests that subquadratic models, including SSMs, might have fundamental limitations. They might struggle to perfectly solve certain tasks that inherently require quadratic time complexity, like very precise document similarity calculations. There's a connection to something called the strong exponential time hypothesis, Seth.
Okay, some theoretical limits.
And there are also ongoing challenges related to complex function composition and multi-step reasoning. Some studies suggest they might struggle with tasks requiring intricate logical steps or function nesting.
So reasoning might still be a weak spot.
Potentially, compared to, say, NSAI's focus. In computer vision, there are efforts to enhance the inductive bias, the inherent assumptions built into the model to better capture spatial relationships, which CNNs are good at. HRV Mamba is one attempt there.
Right, giving it better spatial sense.
Interpretability is another active area of research, with investigations into the grokking phenomenon observed in Mamba, where the model suddenly generalizes after seeming to just memorize.
Yes, grokking.
And researchers are continuously working on improving the stability and initialization schemes for these models to make training more reliable.
And how do SSMs factor into the broader pursuit of AGI?
Well, their capacity for scalable sequence understanding and efficient memory management is undoubtedly a crucial component for AGI. You need to handle long histories.
Sure.
The grokking phenomenon, if better understood, is also highly relevant to the development of more robust AI generalization. However, it's important to recognize that efficient sequence processing alone won't be sufficient to achieve AGI. We still need to address fundamental challenges like common sense reasoning and a deeper understanding of the world.
Right.
The prevailing view seems to be that SSMs like Mamba will likely be a vital building block within a more comprehensive AGI architecture, but not the whole story.
Okay, so we've delved into 3 of the most talked about next-generation architectures, but our sources also pointed towards other promising directions. Let's briefly explore some of those, starting with memory-centric architectures. The name is quite descriptive, but what's the underlying motivation?
The motivation is precisely what the name suggests: to overcome the limitations of memory handling in current architectures, particularly transformers.
The context window problem again.
Exactly. Standard transformers have that fix5 context window and a relatively simple mechanism for dealing with past information. Human intelligence, in contrast, relies on much more sophisticated and dynamic memory systems: short-term, long-term, episodic, semantic.
Right. Much richer.
And Google's Titans architecture is a prime example of trying to address this, isn't it?
Yeah.
That idea of AI that can learn to memorize at test time is a really compelling concept.
It really is.
Titans apparently incorporate a deep neural long-term memory module alongside the more traditional short-term attention mechanisms. They're designed to mimic how humans learn to retain important information and forget irrelevant details over time using surprise mechanisms.
Surprise mechanisms? Interesting.
Reports suggest they can handle incredibly long sequences, exceeding 2 million tokens.
2 million.
And have demonstrated strong performance across various tasks, including language understanding, common sense reasoning, genomics, and time series analysis.
Okay, that's serious scale.
And we're also seeing other interesting approaches like retrieval augmented transformers, which pull in external knowledge.
Arrayed models, yeah.
Raptor, with its hierarchical memory structure, memory mosaics, compressive transformers, all focused on tackling those memory bottlenecks. The overarching goal is to enable AI with much longer and more flexible memory capabilities.
Next up, capsule networks. These have been around for a few years, conceptually at least, but what's the core principle and where are they finding renewed interest?
The core idea behind capsule networks, championed by Geoff Hinton originally, is to represent entities not as single scalar activations, like in traditional neural networks, but as vectors capsules.
Vectors, Crane.
These capsules can encode various properties of an entity, such as its pose, orientation, texture, etc. This allows them to model part-whole relationships and spatial hierarchies in a more robust way.
Part-whole relationships, like understanding a face is made of eyes, nose, mouth in the right configuration.
Exactly, that kind of hierarchical structure. We're seeing them find niche applications, particularly in areas like medical imaging for tasks like detecting COVID-19.
Medical imaging makes sense.
As well as in speech-emotion recognition, intrusion detection and cybersecurity, human activity recognition, 3D pose estimation, and even identifying deepfake videos.
Okay, specific niches.
Their advantages include improved understanding of spatial relationships, greater robustness to changes in viewpoint because the capsule encodes pose, and the potential for learning effectively from less data. The main challenges remain their computational costs and scalability to very large, complex data sets. They haven't really broken into the mainstream foundation model space yet,
Right.
but they hold promise for enhancing AI's ability to understand objects and scenes in a more structured way, which could be relevant for AGI's visual perception.
And finally, hyperdimensional computing. This sounds quite different from the other architectures we've been discussing.
It is a fundamentally different computational paradigm. Hyperdimensional computing, or HDC, utilizes very high-dimensional binary or bipolar hypervectors to represent information. Think thousands or tens of thousands of dimensions.
High dimensions, okay.
And it relies on simple, bitwise operations like binding, like multiplication, bundling like addition, and permutation for processing these vectors.
Simple operations.
Very simple. Its advantages include incredible energy efficiency due to the simplicity of the operations, the ability to learn effectively from small amounts of data, inherent robustness to noise, and very fast learning speeds.
Energy efficient and fast learning. Sounds good for the edge.
Exactly. It's being explored for applications in edge AI devices, healthcare diagnostics where data might be limited, fraud detection, and even cognitive modeling, trying to mimic aspects of human memory. The key insight is that it offers a lightweight and efficient approach to implementing intelligence in resource-constrained environments. It's a different way of thinking about computation.
This has been a whirlwind tour of the AI architecture landscape. It's clear we're moving beyond a single dominant model. Maybe we can try and briefly summarize how these different approaches stack up.
Absolutely. It's a lot to take in. If we consider the core principles, transformers use self-attention. NSAI integrates neural learning with symbolic reasoning. LNNs embrace continuous time dynamics. SSMs offer efficient sequential processing through selective state spaces. Memory-centric architectures focus on enhanced long-term memory. And capsule networks use vector representations for better hierarchical understanding. HDC is different again with its hypervectors.
Right. And their strengths.
NSAI shines in reasoning and potential interpretability. LNNs excel in adaptability to dynamic real-time data, especially irregular data. SSMs are powerhouses for efficiently handling very long sequences. Memory-centric designs aim to break context limits. Capsule networks offer better spatial understanding and viewpoint robustness. HDC is great for efficiency and small data.
And the flip side, limitations.
Well, NSAI faces integration and scalability challenges. LNNs have training complexity and scaling issues. SSMs might have theoretical limits on certain tasks and reasoning gaps. Memory-centric designs are still complex and evolving. CapsNets struggle with scale and cost. HDC is maybe less suited for very complex pattern recognition compared to deep nets.
Okay. And thinking about AGI potential.
NSAI's reasoning focus and memory-centric approaches seem key for higher-level cognition. LNNs and SSMs provide crucial infrastructure for processing complex, continuous, long-form data efficiently. CapsNets could help with robust perception. It really feels like pieces of a puzzle. It's unlikely any single one is a magic bullet.
It really sounds like the future of AI will be a much more diverse and specialized ecosystem of models, less monoculture.
That's a key takeaway, I think. The dominance of a single architecture like the Transformer is likely giving way to a more heterogeneous landscape. We'll probably see more specialized models tailored for specific tasks.
All right.
And, very importantly, a rise in hybrid approaches.
We mentioned some already.
Yeah, we've seen examples like the hierarchical neurosymbolic decision transformer, hybrid Mamba transformer models like Jamba, Goldfinch, RWKVX. There's also the potential for integrating LNNs into broader systems, utilizing retrieval augmented language models, RAG, more extensively, and seeing memory-centric designs like Titans incorporate attention mechanisms.
Makes sense. Combine the best myths.
Exactly. The rationale is clear. By combining the strengths of different architectures, we can mitigate their individual weaknesses and create more robust and capable AI systems. Modularity is likely key.
So, in light of all these new architectural options, how do we need to reevaluate our trajectory towards AGI? Has the path changed?
We're definitely witnessing significant progress in key areas that were bottlenecks before reasoning with NSAI, continuous learning with LNNs, scalable sequence processing with SSMs, long-term memory with memory-centric designs. That's undeniable progress. However, as discussions at AGI 25 underscored, no single architectural innovation is likely to be the complete solution for AGI. Fundamental challenges such as achieving true common sense understanding, robust unsupervised learning, embodiment, maybe even consciousness, these remain huge hurdles.
Right, the really hard problems.
These next-generation architectures represent crucial steps forward, powerful new tools in the toolkit. But achieving AGI will likely require further significant conceptual and technical breakthroughs beyond just architecture.
Finally, looking beyond the specific architectures themselves, what are some of the overarching challenges that we need to address to successfully adopt these next-generation AI systems? It's not just about the algorithms, is it?
Not at all. Data governance, for instance. Ensuring high-quality and unbiased data sets will be absolutely fundamental, regardless of the underlying architecture. We need robust frameworks for managing the data that powers these systems. Garbage in, garbage out still applies, maybe even more so.
Definitely. And privacy, security.
Paramount. As AI becomes more powerful and integrated into our lives, these concerns escalate. We'll need to address potential new vulnerabilities in these novel architectures and prioritize things like encryption, access controls, monitoring, and privacy-enhancing technologies. AI governance becomes crucial.
How about just getting them running? Infrastructure integration.
Big challenge. The computational demands, compatibility with legacy systems, scalability requirements both in the cloud and increasingly at the edge, data storage, all need careful planning. The deployability might even influence which architectures get adopted most widely.
Makes sense. And the cost, justifying it.
Yeah, the financial justification and ROI. There are often high upfront costs for development and infrastructure. Demonstrating ROI, especially for long-term AGI-related research, can be difficult. Organizations need strategic approaches, focusing on high-value use cases, pilot projects, and really evaluating the total cost of ownership.
And finding people who actually know how to build and use this stuff.
The talent and expertise gap. It's real. There's a shortage of skilled professionals, especially with specialized knowledge in these newer architectures. We need more interdisciplinary skills, and the pace of innovation is often outpacing talent development. Investment in education, upskilling, and collaboration between industry and academia is vital.
And last but definitely not least, ethics.
Absolutely critical. Bias and fairness, transparency and explainability, accountability, safety and robustness, human oversight, societal impact. These aren't afterthoughts.
Okay.
Ethics must be foundational throughout the AI lifecycle, from design to deployment and beyond. It requires constant attention and interdisciplinary collaboration.
It sounds like the technological advancements are just one piece of a much larger and more complex puzzle. So to bring our deep dive to a close, what's your overall perspective on this shift beyond the Transformer? Where are we headed?
I believe we're entering a truly dynamic and really exciting phase in AI development. The limitations of the Transformer, paradoxically, have acted as a catalyst for this incredible wave of innovation.
Yeah, necessity is the mother of invention.
Exactly. And we're seeing remarkable progress across various alternative architectural paradigms: integrated reasoning, continuous dynamics, efficiency, reimagined memory, totally different frameworks like HDC. The AI landscape beyond 2025-2026 is likely to be far more architecturally diverse.
A richer ecosystem?
Yes. With transformers potentially coexisting alongside more specialized and efficient models, these new architectures hold significant promise for advancing things like agentic AI, systems that can act autonomously. We should anticipate continued rapid advancements.
And what are some key areas that deserve particular focus as we move forward? Where should research and strategic effort go?
We'll definitely need to deepen our understanding of neurosymbolic integration and make real progress in areas like metacognition for NSAI.
Okay.
Further theoretical and practical advancements in liquid neural networks and state space models are crucial. Refining them, scaling them, understanding their limits. The development of standardized benchmarks that can effectively evaluate AGI-relevant capabilities across different architectures is essential. We need better ways to compare apples and oranges.
Good point. Better yardsticks.
Fostering interdisciplinary collaboration between researchers in different fields. AI, neuroscience, cognitive science, physics, materials, science for hardware will be key.
Break down the silos.
Investing in hardware co-design that's optimized for these new architectures will be important to unlock their full potential.
Hardware matters.
And fundamentally, we need to prioritize the development of ethical, safe, and trustworthy AI systems across the board. That has to remain central.
Absolutely.
Finally, the exploration of hybrid and modular AI architectures seems like a very promising avenue. Combining the strengths is likely the way forward for many applications.
So it seems the journey beyond the transformer isn't just about finding a single superior model. It's more about cultivating this rich and diverse ecosystem of AI architectures, each with its own strength, its own niche, perhaps. Ultimately pushing us closer to more powerful, robust, interpretable, and hopefully more capable AI systems, and perhaps one day to a deeper understanding of intelligence itself.
That's the hope.
It certainly makes you wonder which of these architectural shifts you, our listener, find the most compelling and what the next 5 years hold for this rapidly evolving field. It's going to be fascinating to watch.